This is lecture 2 of condensed matter physics 1. So, let me start by reminding you what we did yesterday. Yesterday, we calculated DC conductivity of a metal using Drude model, and we got sigma naught is equal to n e square tau over m electron. I used a single particle equation and I also used Boltzmann's transport equation. And this was done under relaxation time approximation. I just want to make one correction. Yesterday, I took F R V T for Maxwell-Boltzmann distribution to be beta m over 2 pi raised to 3 by 2 e raised to minus beta m v square by 2. What I forgot here was to put the density out here. So, n should actually be there. So, I have F R V T equals n, the number density of electrons, beta m over 2 pi raised to 3 by 2 e raised to minus beta m v square by 2. So, with that correction, now we move forward and want to see what happens when I apply an AC field to a conductor. Now, before we do that, I would like you to keep some numbers on your fingertips as we go along. So, yesterday we had seen that resistivity of metals at room temperature is of the order of 10 raised to minus 7 ohm meter or 10 micro ohm centimeter, and therefore, conductivity is going to be of the order of 10 raised to 7 Siemens. From this, we will guess or estimate what the collision time is going to be. So, I have sigma equals n e square over m e tau. You combine these two and you get tau to be of the order of 10 raised to minus 14 seconds. So, that is the collision time we are talking about. When these electrons are moving in a solid, they perform a collision every 10 raised to minus 14 seconds. Keep this number in mind, because this will be useful for something I am going to do a little later. So, if I take this tau, let me write collision is equal to roughly 10 raised to minus 14 seconds, then frequency of collision is of the order of 10 raised to 14 per second. All right, this frequency also I want you to keep this number in mind. Now, let us go to applying an AC field to a conductor, and that will give us some properties of this which are related to its optical properties. So, that is the connection I want to make. Recall the equation that we had for the velocity of electron, which was dV dt plus v over tau equals minus E over m. And for DC, in a steady state, we had taken dV dt equals 0. But now I am not doing that. What I am doing now is applying a field E, which is time dependent. So, this is equal to some E naught complex number e raised to minus I w t. Just a note here, I am using complex notation. Finally, its real part matters. So, I would request you to go back and brush it up. So, when I apply this E field, what is happening is these electrons are going to see this oscillating field, and therefore, they are going to go back and forth. Finally, their velocity, therefore, I can take to be time dependent as some V 0 e raised to minus I omega t. dV dt is no longer 0. Electrons are oscillating, and therefore, dV dt is going to be minus I omega e raised to minus I omega t, and there is this V naught floating around. You substitute this in, and then I get minus I omega plus 1 over tau is equal to minus E 0 over m. There is a V naught here. This is the equation that gives me how velocity is going to change. So, I have minus I omega plus 1 over tau V 0 is equal to minus E over m E 0. There is this time dependence e raised to minus I omega t that I have cancelled from throughout. And this gives V 0 equals minus E tau over m 1 minus I omega tau E 0. That is the velocity. So, I will give you a question at this point. The question is, what does imaginary part of velocity indicate? Therefore, the current J is going to be equal to n E square tau over m electron, like it was earlier. Now, I have this new part minus I omega tau E 0 e raised to minus I omega t. By definition, this part is the conductivity, and therefore, I have AC conductivity sigma omega equals n E square tau over m E 1 minus I omega tau, which is nothing but sigma 0 over 1 minus I omega tau. Sigma 0 is DC conductivity. So, what we have seen is that if I apply an AC field to a conductor, the conductivity depends on omega and is no longer a real number. It has a complex part. Let us look at two different regimes of this. One is omega tau is much less than 1. Remember, tau is of the order of 10 raised to minus 14. So, this means I am talking about frequencies omega which are much less than 10 raised to 14 or 15. So, they are maybe in visible, infrared, microwave and whatever. And the other extreme is omega tau is much greater than 1, which means omega is much greater than 10 raised to 14 or 15. And we are talking about electromagnetic waves or frequency of the order of ultraviolet or X-rays. What happens in these regimes? I have sigma equals sigma 0 over 1 minus I omega tau. So, sigma for omega tau much less than 1 is pretty much like sigma naught. So, your material is behaving like a regular conductor, it will heat up and things like those. And the other regime I have is sigma for omega tau much greater than 1, and this means sigma omega, I have already written sigma omega, is equal to sigma naught over minus I omega tau, which is equal to I sigma naught over omega tau. So, let me again ask you a question. For omega tau much greater than 1, sigma omega is purely imaginary. Will the material have Joule heating? Think about it. How would you work it out? And as I had said earlier, what finally matters is the real part. So, you got to calculate the current density multiplied with E, averaged over the time period, and see if there will be Joule heating. If there is no Joule heating, what happens with high frequencies? So, let us see what happens physically. Remember, what is happening is I have this material, although this is not a correct picture, but according to the model this is the picture. In this, electrons are moving around, they are whizzing around, and then they have this drift velocity. Now, they have this going back and forth motion, and at very high frequency, right, at omega tau much greater than 1. The electron oscillates many times before having a collision. So, this electron is moving back and forth and it does not collide. If it does not collide, physically you see there will be very little Joule heating, because finally the resistivity or this loss of heat comes because the electron loses its velocity, its drift velocity, once it collides. So, that is not happening anymore. But what I want you to do is, in this problem here, show it mathematically. This will help you in connecting this physical picture with the way you do mathematics with these imaginary numbers and what does sigma omega mean and all that. So, this is what we have derived. Now, I am going to spend the rest of the lecture discussing the implications of this. So, what I have now is sigma omega equals sigma naught over 1 minus I omega tau. and I want to discuss its implications. As far as this solid conductor is concerned, and that is the connection we are making now. Now, recall from your electromagnetic course that we talk about if I have this conductor and I put some extra charge on it, right. So, I put this extra charge, and the question we ask, how long does it take for this charge to distribute over the conductor? This is something you all have done, so I will just repeat it. What we do in this case is we write the continuity equation d rho dt plus del dot j equals 0. I put j equals sigma e. So, I get d rho dt plus sigma del dot e equals 0, and therefore, d rho dt plus sigma over epsilon rho equals 0. And what one argues from here is that rho t therefore is some rho 0 e raised to minus I t over tau, and this is tau for relaxation. This is not tau collision. So, this tau is epsilon over sigma, which would be 10 raised to minus 11 divided by sigma is of the order of 10 raised to 7. So, this is 10 raised to minus 18 seconds. This is what you have learned from your course in EM theory. You learned from Griffiths, that is 10 raised to minus 18 seconds. It should actually ring a bell in your head. There is something wrong we are doing, right. So, this charge dissipates in 10 raised to minus 18 seconds, and how are we getting it? This comes from sigma for which tau collision is 10 raised to minus 14 seconds. So, we are saying it dissipates even before it has collided. There is something wrong in it, right. I am calculating a quantity conductivity using a time scale of 10 raised to minus 14 seconds, and then claiming that based on that I am getting a time scale of 4 orders of magnitude smaller. There is something wrong, right. So, something is wrong. This is not quite right. There is an inconsistency. And the way it is resolved is if I take sigma to be omega dependent, because when this charge is dissipating in such a short time, it has all sorts of Fourier components, and each one behaves differently. So, let us do that calculation. So, what this tells me, the inconsistency in time scales implies that should use sigma omega. I had used sigma dc there and I got a wrong answer. So, if I do that, what do I get? I get d rho dt plus sigma omega over epsilon rho equals 0. I get d rho dt plus sigma omega is sigma naught over epsilon naught 1 minus I omega tau, and this is tau collision, rho equals 0. Let us look at the solution for this such that rho is some rho 0 e raised to minus I omega t. So, oscillatory solution. Then d rho dt is minus I omega rho. So, if I substitute this in the equation, I get minus I omega plus sigma naught over epsilon naught 1 minus I omega tau equals 0. And that gives me what those eigenfrequencies omega should be. If I take everything in, I get minus I omega plus minus omega square tau plus sigma 0 over epsilon 0 is equal to 0. I get omega square tau plus I omega minus sigma 0 over epsilon 0 equals 0. That is my working equation for this omega. Let us find out what it is. The solution then is omega equals minus I plus or minus square root of minus 1 plus 4 sigma naught over epsilon naught divided by 2 tau. Remember, sigma naught over epsilon naught is of the order of 10 raised to 7 over 10 raised to minus 11, 10 raised to 18. So, I can ignore that 1 in front of it. Therefore, the solution I get is omega equals minus I plus minus square root of 4 sigma naught over epsilon naught over, there is a tau also floating around, 2 tau. Was there tau? No, there is no tau, sorry. Okay. Which is minus I over 2 tau plus minus 1 over 2 tau square root of 4 sigma 0 over epsilon 0 which is minus I over 2 tau plus minus 1 over tau square root of sigma naught over epsilon naught. Let me see, I think I am missing a tau. Let me just check. Going back, there was a tau here, yes. There was a tau here. So, okay, there was a tau sitting here. There was a tau sitting here. Okay, now let us calculate this quantity. Sigma naught tau over epsilon 0 is n e square tau over m e epsilon 0 times tau. If I take tau inside, I get omega equals minus I over 2 tau plus minus omega p. I am just identifying a quantity omega p, which I will call plasma frequency. I will explain why it is called plasma frequency, where omega p square you can check easily from here is n e square tau cancels over m e epsilon 0. So, this charge density rho t is like rho 0 e raised to minus t over 2 tau e raised to plus minus I omega plasma t. Now, you see this whole thing makes sense. The charge density goes down at the same time scale as the collision. It cannot go down faster because collisions that bring it to equilibrium. That is what relaxation time approximation is all about. That is what this tau means. The moment they have collision, the charge density comes back to, tries to come back to its equilibrium situation. But at the same time, it is oscillating with this. So, what is happening is, I create in this metal a charge density. This charge density slowly comes down, but comes down oscillating. So, this charge density you will see something like this. What I have shown you that in a conductor, through this model, what we have observed is that this can sustain oscillations of frequency omega p, which are known as plasma frequency. Let us just find out what the the range or the scale of omega p is. So, these frequency omega p square is n e square over m epsilon 0 10 raised to 28 29, e square is 10 raised to minus 38 divided by m of the order of 10 raised to minus 30, epsilon 0 10 raised to minus 11. So, that gives you 10 raised to minus 41, 10 raised to 3 of the order of 10 raised to 31. So, omega p you can say is of the order of 10 raised to 15 to 10 raised to 16 radians per second, which is on the upper end of the optical frequency or in ultraviolet. So, these oscillations occur in ultraviolet. All right, now let me show this in a slightly different manner, doing electrodynamics for conductors, and then you will see that these are really oscillations that can be sustained, and we will see how they are observed experimentally. So, if I want to do electrodynamics, I have divergence of E in this as rho over epsilon 0, divergence of B equals 0, curl of E equals minus dB dt, curl of B equals mu 0 j, which I will write as sigma omega E plus mu 0 epsilon 0 dE dt. I will connect this with plasma frequency. I will look for solutions E like E 0 e raised to minus I omega t. For travelling wave, I will look for E r t as E 0 vector e raised to I k dot r minus omega t, and B similarly would be B 0 e raised to I k dot r minus omega t. I am looking for these solutions. And the great advantage of using this complex notation is that I can replace all these divergence and curl with k dot k cross and time dependence by minus I omega, and therefore, if I look at these equations now, they are I k dot E equals rho over epsilon 0, I k dot B equals 0. So, k dot B is 0, I k cross E is equal to minus will become plus I omega B, and I k cross B is equal to mu 0 sigma omega E minus I omega mu 0 epsilon 0 E. These are my 4 equations. I will look for their solutions standard way. So, I will take this equation here and do a k cross E, which will be equal to omega k cross B, and k cross B I can substitute from here. The left hand side is nothing but just by vector identity k dot E minus k square E, and right hand side can be worked out. I worked it out, I leave it for you. So, what you get finally is that from the left hand side you get k dot E minus k square E, and right hand side when you work it out, what you get is omega square mu 0 epsilon 0 1 minus omega p square over omega square E. Along the way, I have taken omega tau much greater than 1, and therefore, I have taken sigma omega to be sigma 0 over omega tau times I. All right. So, I am working at very high frequencies compared to that collisional frequency, then I get this. Now, look for solutions E that is parallel to K. If I am looking for E which is parallel to K, and that means I am looking at longitudinal oscillations. K is in the same direction as the displacement. Then the left hand side is 0. Why? Because K and E are parallel. So, everything K square E comes on the left on both the terms. And this implies that for this to be possible, the left hand side is 0, the only term that can be 0 on the right hand side is this, or omega equals omega p. So, what we have seen is that if I have a conductor, the electrons can have oscillation, longitudinal oscillation at omega p. All right, these are known as plasma oscillations. And beauty here is that the associated magnetic field is identically 0 in these. So, plasma oscillations have E parallel to K and B equals 0. Show this. E parallel to K, I have already shown this. Let us just look at it physically, and this is a very standard problem. If I have a metallic block, positive uniform charge, and I displace the electrons by a small distance here, so that this is all negative charge, this is all positive charge. There will be a field inside like this, which will pull these electrons back, and this whole block will oscillate with omega p. Okay, I want you to show this. Should make it thicker. All these purple boxes are for you to work out. This is a standard problem. So, this is a collective oscillation. So, electrons perform collective oscillations, and these are longitudinal of omega equals omega p. That is number 1. What about transverse waves? That is EM waves for which K is perpendicular to E. So, again you go back to this equation that we had K dot E minus K square E equals omega square mu 0 epsilon 0 1 minus omega p square over omega square E. This gives you K dot E is 0 because K is perpendicular to E, and therefore, k square comes out to be mu 0 omega square minus omega p square. There is a minus sign somewhere. I'll leave it for you to check. I may have messed it up somewhere. All right. And therefore, k, or this mu epsilon is also not there. K is equal to mu 0 epsilon 0 square root omega square minus omega p square, which is 1 over c square root of omega square minus omega p square. So, k is imaginary for omega less than omega p and real for omega greater than omega p. So, I found that k is equal to 1 over c square root of omega square minus omega plasma square. This is the dispersion relation for electromagnetic waves. So, what you will have is, in a conductor, the wave would not propagate for frequency omega less than omega plasma. This is k. And far away, the relationship will become linear. The way it is shown in the books is that you plot omega versus k, and you show that below omega p, there is no propagation, and this plasma frequency goes like this is the relationship. So, if you have a metal on one side, for omega less than omega p, you will have decay here. For the other wave, you will have them going through. And that makes sense, because physically what is happening is, if omega is less than omega p, now recall what I did earlier. For omega less than omega p, and that is my scale. So, when I say that omega tau is much less than 1, which basically would come out to be omega is much less than omega p. In that case, electrons are colliding, they are taking away energy, I am losing energy, and therefore, the wave just dies down on the metallic side, and therefore, there is a huge reflection. On the other hand, when omega is greater than omega p, omega tau is much greater than 1, right, implying that omega is greater than omega p, this guy transmits through and reflection is low. So, when you do experiments, what you find is, if you plot reflectance versus omega, you find almost perfect reflectance to start with. It comes down, goes to 0 at omega p, picks up again, and never goes back to 1, but something like this. All right, this is a property of metals. This is one way you can find what omega p is. Okay, so that's the electrodynamics of it. The other point I made was that they are sustaining longitudinal oscillations, right. So, two things we have learned from this. Sigma omega gives you 1 plasma oscillations, 2 reflectance dependent on omega. So, how do I observe plasma oscillations? That is also a very nice experiment to do. What is done is, if these are oscillatory modes, they will have energy h cross omega p, 2 h cross omega p, 3 h cross omega p, and so on. And therefore, if I take a thin film, metallic film, and shoot electrons through them, electrons come out after losing some energy. And if you plot how much energy do they lose as a function of omega, this is loss, you get peaks at constant intervals. And these peaks differ by h cross omega p. So, either the system can take one quantum of that oscillation, two quantum of those oscillations, three quantum of those oscillations, and so on. This is all simply from that Drude model and its omega dependent conductivity. Now, let me give you some numbers. Data on loss spectrum of electrons. So, I will give you the metal, then experimental h cross omega p, theory h cross omega p. Lithium, experimental h cross omega p comes out to be 7.12 eV. Theory predicts 8.02. Sodium, experimental comes out to be 5.71 eV. Theory gives you 5.95. Potassium, I get 3.72 eV. Experiment is 4.29. Magnesium, 10.6 eV. Experiment is 10.9. And finally, one more, I am going to give you aluminum, which is 15.3 eV and 15.8. So, you notice that the first three elements, the alkali elements, there is some discrepancy between theory and experiment, although they are close. They are close to about, within 10 to 15%, but slight discrepancy. Mg and aluminum, that is not the case. But it is very satisfying to see that whatever numbers come out from theory are close to experiments. Other thing you notice is that plasmon energy is of the order of 10 eV. It is very high energy, right. So, this is what solids do. Now, the difference arises. So, once you have digested these numbers, right, we will say that the difference in experiments and theory arises due to relative dielectric constant of the material. How so? Remember, I wrote omega p square equals n e square over m e epsilon 0. If this is slightly higher, if instead of epsilon 0 is some epsilon relative epsilon 0, where epsilon relative is greater than 1, then you would have omega plasma frequency, which is slightly smaller, and that is precisely what happens. The epsilon relative arises because of the background ions, right. So, what I like you to do now is estimate epsilon relative for Li through k using h cross omega p data. Other thing I like you to do is estimate the electron number n from the data and compare with standard one given in the books. The books are those that I have prescribed. And again, explain if there is any difference. So, let me now conclude this lecture by stating that we have looked at frequency dependent conductivity of metals sigma omega, and from that we understood that metals can have longitudinal plasma oscillations determined by epsilon omega equal to 0, and third, for omega less than omega p, light or EM wave gets perfectly, and I am using this within quotes, reflected from metals. So, this is the property of these solids, and gets transmitted for omega greater than omega p. You see this all the time. I mean, you see that mirrors use a silver film on the back side. You see a lot of metals, when sun shines on them, you see a lot of reflection, whereas X-rays pass through them. So, with this I conclude this, and next lecture I will do Hall effect and start on thermal properties. Thank you.